Hi everyone, this is Mrs. G.A. and today is day 2 of curve sketching. Alright, I have a warm up for you guys, so please pause the video and give it a try. Alright, go ahead and check your work here. So remember, for vertical asymptotes, we're essentially looking for times when our denominator is equal to 0, because that's when our function is undefined. And then you can determine horizontal asymptotes if they exist by finding the limit as x approaches infinity. So for parts A and B, when you do that, you'll see that the graph approaches infinity on the right and negative infinity on the left. So there's no horizontal asymptote. But here we can do a little long division to find the equation of our slant asymptotes here. And then for part C, if you factor the numerator, you'll see that this factor of x plus 1 actually cancels out. So that's not going to create an asymptote. It's actually just going to create a hole at when x is equal to negative 1. So there's actually no vertical asymptotes here. And if you look at our end behavior, the limit as x approaches positive or negative infinity, in this case both sides go up, is really all you have left is this quadratic function. So it's just a quadratic function with the hole at x equals negative 1. So I wouldn't necessarily say that it has a slant asymptote because there's no linear equation that it's following, but here it's just, again, a quadratic with the hole at x equals negative 1. So here is, again, just a quick recap of what we talked about in the warm-up. So how you can determine where vertical asymptotes occur, essentially values where the denominator of a rational function is equal to 0 with no canceled factors like we saw in part C. And horizontal asymptotes are just end behavior. So it's the what's happening when x approaches positive or negative infinity. So as we did in the warm-up, we can determine horizontal asymptotes by taking the limit as x approaches positive or negative infinity, but with rational functions, there was also some tricks that we learned in pre-calculus for finding horizontal asymptotes. And it was essentially memorizing 3 rules when you compare the degree of the numerator and the denominator. So remember, if the degree of your numerator is less than the degree of your denominator, so that would be the first case, we know that our horizontal asymptote will be y equals 0, because essentially you're just dividing by a much larger value than you have in the numerator, and when your denominator is larger, you're dividing by that larger number, that value is just going to get closer and closer to 0. So you can memorize that rule. Of course, we could do this with limits. So remember, what we learned to do is we learned to divide each term by the largest degree in the denominator. So we would essentially divide each term by x to the 4th, and then we have limits that will approach 0. So we would end up with 2 over x squared minus 1 over x to the 4th over 3, just 3 in the denominator. So this value right here, this would approach 0 because your denominator is getting extremely large, so this will approach 0, this will approach 0, and what you have left is 0 over 3. Which is just 0. So we can do the same thing with the limit process, or we know if the degree in the denominator is larger, the horizontal asymptote will be y equals 0. And you'd maybe have a graph that looks something like this. Lots of different cases of what it could look like, but that's just one example, or that's the example that goes with this particular function. The second case was, well, what happens if the degree of the numerator is equal to the degree of the denominator? Kind of the general idea behind this is when you plug in an extremely large number, everything cancels out. These values here are so incredibly small compared to these that we almost ignore them. The x squareds almost cancel out, and we're just left with the ratio of the leading coefficients. But again, you could also evaluate this with limits. If you divide each term in the numerator and denominator by x squared and take the limit as x approaches positive infinity. So it leaves you with 3 minus 2 over x over 4 minus 3 over x. So this portion will approach 0, this portion will approach 0, and you can see that when we know that the limit of a constant is just the constant. So you're left with 3 over 4. So here's a picture of this graph here, so you can see that it does approach that line 3 over 4 to the left and the right, so as x approaches positive or negative infinity. And then our last case was what happens when the degree in the numerator is larger than the degree in the denominator. Well, that means just, the top is growing faster than the bottom. So you're just going to keep growing without bound. So that's where you won't have a horizontal asymptote, but you will have a vertical asymptote or a slant asymptote. But again, we can evaluate this with the limit process. So if I divide each term by x, remember it's always the largest degree of your denominator, leaving you with x minus 1 over x over 3. This approaches 0, and then it's infinity over 3, which is just infinity. But again, in this case, this is when we would do our little long division, and you would end up with a slant asymptote. So we would have x squared, I'll say plus 0x minus 1. So here, if you have x squared divided by 3x, we actually end up with 1/3 x. So when I multiply those together, we have x squared, we would subtract, well, the 0x is just going to give us another 0 term, so we can actually just bring down the -1. And from here, there's nothing left for us to divide into, so our slant asymptote equation is simply the quotient, so it's y equals 1/3 x. So remember, we don't worry about the remainder when we're finding that slant asymptote equation. And then it generates a graph that looks something like this. That's the graph of this particular function. And then just an additional reminder that while it is never, ever, ever okay to touch or cross a vertical asymptote, it is completely fine to cross or touch a horizontal asymptote or a slant asymptote. It's very common for the graphs to cross over, maybe once or even multiple times, but eventually they will approach the asymptote as x approaches positive or negative infinity. But again, horizontal asymptotes just describe end behavior. So what's happening in the middle, it could cross a bunch of times, but towards the end it will eventually approach. So it is okay to cross a horizontal or slant asymptote. All right, so now we're going to try our entire curve sketching process with a rational function. So always a good place to start would be to determine our domain and then any zeros that we might have. So we can see here that our domain, we do have a restriction. We can see because of the denominator that x cannot equal 2. So that's going to be something to consider as we're graphing. And then for the intercepts, we would set our numerator equal to 0. So remember, or for the x-intercepts, a fraction is 0 when your numerator is 0. So we could say 0 equals x squared plus 12. But here we know this would generate imaginary numbers. So this will never equal 0, which means that for this particular graph, we actually have no x-intercepts. But we can also try to find some y-intercepts. So we substitute x with 0. So we get 0 plus 12 over 0 minus 2. So we get -6. So we do have our y-intercept at 0, -6. The next thing we would want to look at, because it is, again, a rational function, what asymptotes we have, if any. So I can see here, remember we do have that vertical asymptote at x equals 2. So we can sketch that into our graph, but we are going to want to know what our graph does as it approaches that asymptote. So we're going to take the limit as x approaches positive 2 from the left and the right. So let's start from the right. So for this, remember, we imagine that we substitute something that is just larger than 2, maybe like 2.001. So our numerator would end up being positive if we do that. And our denominator would also be positive because we have something a little bit bigger than 2 minus 2. So this will approach positive infinity. So to the right, it's going to go up, or on the right, it's going to go up. And then we'll do the limit as x approaches 2 from the left. So again, imagine a value that is just smaller than 2. So our numerator will still be positive, but in this case, our denominator will end up being negative. So this limit will approach negative infinity. So it's going to go down as it approaches from the left side. So we're going to tie that into our graph later on, but it's all just stuff to consider. And then we also know that since the numerator, the degree of the numerator is larger than the degree of the denominator, we will have a slant asymptote. So we do need to do a little division. You could do long division here, or we could actually do synthetic division. It's probably a little quicker. So we have 1, 0, 12. And so our slant asymptote, slant, is y equals x plus 2. So we can sketch that on our graph really quick if we would like. So it's just a linear equation that has a slope of 1 and a y-intercept at 2. And there you go. All right, so now we have the key information from our original function, but now we need to move on to the information that we know from the first derivative. And remember, that tells us where a graph is increasing and decreasing, and also it might help us find some relative or absolute maxes and mins. So we need to start by finding the critical numbers, or the critical values. So first we need to find our first derivative, so we will need to use the quotient rule here. So we have low d high minus high. Derivative of the denominator is just 1, all over low, low. So we'll want to multiply this out and combine like terms. So it leaves us with x squared minus 4x minus 12. And we can factor that, actually. So we have x minus 6 times x plus 2 over x minus 2 squared. So remember that our critical values come from when our first derivative is equal to 0, or when our first derivative is undefined. So we know that our first derivative is going to be undefined when our numerator of the derivative is 0. So I can see that there is a critical value at positive 2, because that's when our first derivative is undefined. And then we also would say, when is our derivative equal to 0? So you set the numerator equal to 0. So we also have critical values at 6 and negative 2. So we have 6 critical values. So we're going to use these to help us determine intervals of increasing and decreasing. So we do need to do a little sign analysis. Okay, so we have negative 2, 2, and 6. So whenever we're doing our sign analysis, we see that our denominator, because we're squaring it, will always end up positive. So really, we're just looking at these two factors. So if you plug in something to the left of negative 2, we get a negative times a negative, which gives us a positive. So it's going to be positive in this region. Let's say if you substitute 0, we get a negative times a positive, which gives us a negative. Imagine maybe you substitute 3, you get a negative times a positive, which gives us another negative. So it remains negative. And then if you substitute maybe 7, you get a positive times a positive. So here we can use this to describe our intervals of increasing and decreasing. So our graph is increasing when our derivative is positive. So from negative infinity to negative 2, and then from 6 to infinity. And our graph is decreasing when our first derivative is negative. So that would be from negative 2 to 2, and from 2 to 6. Remember, at 2, our derivative is actually 0, so we wouldn't include it in that interval of decreasing. Now remember, we also use our first derivative to look for relative maxes and mins, and that's going to occur when your derivative changes from positive to negative or negative to positive, because you're either changing from increasing to decreasing, so you'd have a relative maximum, or decreasing to increasing, so a relative minimum. So you can see that the sign is changing at 2 different values. It actually changes at negative 2, and since it's changing, again, from increasing to decreasing there, we see that we're going to have a relative maximum at negative 2. So we'll go back and plug that value into our original function, way back up here into f of x. So f of negative 2 gives us 4 plus 12 over negative 4, so we get negative 4. So we have a relative max at -2, -4. And then you can see that our first derivative is changing from decreasing, or from negative to positive, meaning our original function is changing from decreasing to increasing at +6. So we need to figure out what that value is because that's going to be a relative minimum. So here we have 36 plus 12, so 48 divided by 4 is 12. So we have a relative min at 612. And we can go and plot those on our graph really quick. So we have -2, -4, and we have 612. So that one does go a little bit off our graph. I'm just going to estimate it up here. So that's 612. All right, so now we're done with our first derivative work, but last we need to work with our second derivative, which will help us determine concavity and our points of inflection, which is where we change concavity. So we need to start by finding our second derivative. And I'm going to go from this form of our first derivative. So we do need to do quotient rule again. So we have low, d high, so 2x minus 4 minus high. So we have x squared minus 4x minus 12, and then d low. Remember, we do need to do chain rule here. So 2 times x minus 2 to the power of 1, and then the derivative of the inner part is just 1, and then divided by low, which actually will end up being x minus 2 to the power of 4. We can actually simplify out the factor of x minus 2, at least one factor. So we have x minus 2 times 2x minus 4 minus 2 times x squared minus 4x minus 12 over x minus 2 cubed. And then we're going to multiply this out and keep simplifying. So here we would have 2x squared, and then we have minus 4x, so minus 8x plus 8 minus 2x squared plus 4x plus 8x plus 24 all over x minus 2 cubed. And we can start simplifying our numerator. So these will cancel out, and that just leaves us with 32 over x minus 2 cubed. Now, to help us determine intervals of concavity, we're going to want to know the critical values for this second derivative. So it's either when our second derivative is equal to 0 or undefined. So it's never going to be equal to 0, but it is undefined at x equals 2. So we'll do a little sign analysis of our second derivative at x equals 2, again, because that's when our second derivative is undefined. So anything to the left of 2, if you plug it in, you will get negative. Anything to the right will be positive. So that tells us that our function is concave down from negative infinity to 2 and concave up from 2 to positive infinity. And remember, points of inflection occur when our second derivative is equal to 0. But in this case, our second derivative is never equal to 0. So in this case, we actually have no points of inflection. And that's really occurring because that only critical value is actually when it's undefined. And we know at x equals 2, if you go back up to our original graph way up here, we can see what's happening there. That's actually where our vertical asymptote occurs. So this is essentially saying that everything to the left of our vertical asymptote, our graph is going to be concave down, and everything to the right, our graph is going to be concave up. And so we can go in and finish sketching our graph. I guess the only thing we still need to add that I didn't add at the beginning would be our y-intercept at 0, -6. So right here. And again, we know that our graph is concave down in this area. We know that as x approaches 2 from the left, it approaches -infinity, so that ties together with what we found here. So our graph is going to look something like this. And remember, this value right here is a relative maximum, so you are going to want to make sure your graph doesn't go any higher than that value. Then I'll do something like this. And then we know from our limit here that as x approaches 2 from the right, our graph is going to go up forever. So if I kind of extended out our asymptotes a little bit more like this, and I know that this is a relative minimum, and I know that our graph is concave up in this entire region, I know that our graph is going to do something like this. And remember, that is a minimum, so our graph should not go any lower than this value right here. All right, so here we have a very accurate sketch of our function using our knowledge of the first derivative and the second derivative. Lots of work, but again, curve sketching really allows us to tie everything together that we've learned about derivatives. All right, so that's actually our only example for this video, so that's it, and thank you guys for watching.